Welcome to the session on welded slab base design. In the previous session, we have studied about the bolted slab base. In these sessions, we'll try to understand how to design the end connections, that is the connection between the column and the slab base by welding, and what type of welding has to be done. All these things we'll discuss in this session. Whenever the column is subjected to only a direct load, the axial load, without any moment, we can design the slab base. As per the code specification given page number 46-47 of the code, we can have a look on that and design the size of the base plate. Based on the cutting of the ends, if it is a hand cut or a machine or frame cut, we are going to take the 100% load, whatever that is acting on the column, to be transferred onto the base plate. If this end is cut by machine, also called as grinded ends or milled ends or flushed ends, anything like that, if it is said, then we are going to take the 50% of this load for designing the welding. If the length of the weld available is less than the length required, then we have to go with additional increase in the length of the by providing the stiffness, or otherwise we can design the weld like this, provide all around the periphery of this eye section. As I said, if the length increases, we can provide the stiffness like this and increase the length of the welds like all round and provide it. And sometimes we are going with cover plates like this. Even further out also you can go with the welding, all round peripheral welding. All these weldings we are going to do it either with the shop welding, normally with the shop welding, and many a times we also go with the butt welding also to transfer the load from the column onto the base plate. If this column is subjected to moment also, then we can make use of the angles here, and provide it. Even for the earlier cases, if you are interested, you can use the angles or you can remove it. It is left to the discretion of the designer. When it comes with the moment, it is better you provide the angles here to keep the column in position, intact with the slab base and in position. Now let us study about all these things in by viewing the 3D model created by the AutoCAD software. Now let us go into the AutoCAD session. Welcome to the session on AutoCAD. As I said earlier, when the load is axially acting on the column section, we can have a view of the welding gear. Where a welding has been done all around the column section. This is a high section with the cover plates on either side. It can be with high cover plate or without cover plate. All these things will be given by the given in the examinations, or it is left to the discretion of a designer. We'll have a look on this. Welding. A direct fillet weld to connect the column, the core plate, to the base plate. Provided with the anchor bolts. Let me hide the concrete block. Let me take without cover plate. The column section. All round direct fillet welding. Connecting the column to the base plate like this. And these two cases, what you observed in this AutoCAD will tell you that the length of the weld available is greater than the length of the weld required. You can see the shape of the fillet weld, a convex shape. This is a convex welding, convex fillet weld. If the length of the weld required is greater and availability is less, then at that time we have to provide the additional stiffness, as you observe here, to the column section. All this depends on the availability. Yes. So when the length has to be increased, we are going to provide the stiffness like this, provide the welding this side as well as on the opposite side like this, and increase the length of the weld. This is increased. It depends, whatever the length that is to be accommodated extra, based on that we are going to provide all this stiffness. If you're interested, provide this too or eliminate. Even this, it is nothing but it's simply provided here. The additional length will be carried by this. So like this we are increasing the length of the weld. And from architectural point of view, we have tapered this, cut the section plates like this. It's only from the architectural point of view. I'll show you the plan of this one. Just have a look on the plan. This is a plan where you can see the I section, the additional plates here, and these are the stiffness. Where the length has been increased, you're going to do the welding like this. Let us try to understand all these things by solving a problem, by taking a typical problem and solving it. Hope you understood the different views of this, and there are many more other types of connections are there. We can have a look on all those things in the later session. Now let us try to learn the design of welded connection by taking a problem. Now here we are considering a column section ISHB 300 at 58.8 kg per meter, which carries an axial load of 1000 kilonewton. The allowable bearing pressure of the concrete is given as 6.75 Newton per millimeter square. This is for a M15 grade concrete. The SBC of the soil is given as 1800 kiloton per meter square. This has to be connected by the fillet weld for the two conditions. Let us try to understand how to take the load into consideration for designing the welding. The first one is a direct bearing. The second one, the ends of the columns are not machined. When that is the case, what is the load to be considered, how to go about the design, and let us see that what type of connections to be made at the bottom. As you observed it in the 3D model, what type of connection to be given, let us think about that and provide it over here. Now consider this, take the column section into consideration. The column is ISHB 300 at 58.8 kg per meter. This has to be connected to the slab base by the fillet weld. Either you can go with the butt welding or the fillet welding. In fillet welding, either you can go with the shop welding or field weld. Thus normally the base plate will be connected to the column flanges in the shop itself, in the factory itself. Therefore, we are going to consider the shop welding here. Appropriate partial safety factor has to be taken from the code. We will see that when you continue with the design. Looking into the properties of this ISHB 300 at 58.8 kg per meter from the steel handbook, we are going to get the depth of the section as 300 mm. This is the depth of the section from here to here, and this is the breadth of the section equal to 250 mm, and thickness of the flange equal to 10.6 mm. The dimension of this will tell us that it is rectangular in shape. So we can design a rectangular slab base by two methods. Let us follow any one of the method in this session. The axial load is given as 1000 kilonewton. It has been factored with 1.5 partial safety factor. We get 1500 kilonewton axial load. There is no moment given in this case. Here, if the base plate can be calculated by using the formula factored load by bearing strength of the concrete, and as it was explained in the earlier session, the bearing strength is given by the formula 0.45 times of FCK, F as given in page number 65 and 66 of IS 456-2000 code, and in IS 800 it is given as 0.6 times of FCK, and we are adopting the permissible limit as 0.44 times of FCK in our design here. So bearing strength is 6.75. Let us find out the area of this section. Required area of the base plate is 222.22 into 10 power 3 mm square. Let us design the base plate. The overall dimension of the base plate, as I said earlier, it is rectangular in nature. 300 by 250, it is rectangular in nature. Therefore, we can design a rectangular base plate. In the bolted connection, we have designed that as a square base plate. Here we will design a rectangular base plate by taking this projection, whatever it is there beyond the column, we will take that as the projections. Here also I can take this as A and B, make them equal and design the rectangular base plate. Or I can get the dimension of this, get this to A and B at different value and solve the problem. Any method could be adopted. In this session we are going with equaling the projections. Further, you can look into my notes for different projections here, the larger and the smaller projection. The area of the base plate, it is B into L. This B into L is being equated to the area required. So B is nothing but 300 plus this projection B plus this side projection B. So it is B is 300 plus 2 times of B, and L is 250 plus A plus A. So this is the formula. Now I will take this A and B equal to some capital A, find out the product of this. It is 300 into 250 is 75,000, 300 into 2 times of A is 600A, this is 500A, and 2 into 2A into 2A is 4A square. Solve this quadratic equation, get me the value of A. So we have taken the A as 98.533 mm. I can approximate it to 100 mm. So these are the two equal projections equal to 100 mm. We'll find out the breadth of the section. It is 300 plus 2 times of B. 300 2 times of B is 500 mm. So B is 500 here, and L is 450 mm. The size of the plate without thickness is 500 mm by 450 mm. 500 like this, 450 like this. Let us find out the thickness of the base plate by using the formula given in the code in the clause 7.4.3.1 of page number 47 of IS 800. Let us find out this thickness. So in that clause it's been given as thickness of the slab TS is equal to under the root 2.5 times the upward pressure, W is the net upward pressure, A square minus 0.3 B square into gamma m naught, which is given in the page 30 of the code, divided by Fy, the yield stress of the material. The complete value shall not be less than Tf. It should be always greater than thickness of the flange. Now find out the net upward pressure by using the formula Pu by area of the base plate, which shall be always less than the bearing strength of the concrete given. It's given as 6.75. Now let us find out. It is 6.67 Newton per mm square. Convert this per mm width. It's 6.67 Newton per mm. This is the net upward pressure which will be acting below the base. Using this, we will find out the thickness of the slab. Substitute and the formula Ts, you will get 22.66 mm, which is greater than Tf, that is 10.6 mm. Therefore, we can adopt it. Let me make it a round number, say 24 mm. The thickness of this is 24 mm, and the overall dimension of the slab base is 500 mm by 450 mm by 24 is the size of the base plate. So this procedure is same as whatever we have done it for the bolted slab base. Up here the procedure is same. Now we'll go with the connection details. You got two cases are there, one for the full bearing, other one for the not machined ends. For full bearing means the ends of the columns are cut by machine, it has been grinded. Therefore, the load that will be transferred onto the base slab will be 50% of the column factored column load. It's 1500 by 2 equal to 750 kilonewton. For this 750 kilonewton, you have to design the length of the weld required. Now let us first understand what is the length that is available in the length of weld that is available here. So we are going to weld it here to the outer face of the flange, the inner faces of the flanges, the web portion, the flange, the web. Like this we are going to weld all around the periphery of the column section. Now let us, what is the total length available? You got the length here 250 and 250, it is 2 times of 250. We are going to weld it to the inner side of the flanges. It's totally from here to here 250 minus this width, that is equal to TW 7.6 mm. 250 minus 7.6 is the length on one side. We are going to take two sides. Plus you are going to weld along the length of the web, that is 300 minus 10.6 here, 10.6 here. We are going to get this length equal to 1542.4 mm. Sometimes in some of the books has been given as that it is not possible to weld this portion, that is the root radius, and this toe portion. Therefore, you can eliminate this length to get the effective length of the weld. All these corners are the ends, the toe ends and the root ends. This is a toe end, this is a root radius end. You cannot weld it. Therefore, you can reduce that length, but here which is equal to 2 times of the size of the weld. But here we are just neglecting that and taking it equal to 1542.42 mm is the length available. We know the formula to calculate the strength of the weld. We have studied that in the second module itself. The strength of the weld is given by 0.707 into d into length of the weld into Fu by root 3 gamma mw. So this d is nothing but the size of the weld. We can assume it not less than the 3 mm, and the gamma mw, by assuming the shop welding, we can get the value of the partial safety factor for welding. Now, if you look at the page number 30 of the code table 5, the welds for shop fabrications it's given as 1.25 gamma mw, and for field fabrications it's given as 1.50. So we are doing with the shop welding. I'll make use of that here in the formula as 1.25 and assuming the size of the weld as 8 mm. Now substitute that in the formula. Equate this total strength of the weld to the load that has to be carried. It is 750 kilonewton. We are equating it to this. I'll find out the length of the weld. It works out to be 700.23 mm. This is the length that is required for this load of 750 kilonewton. We already got 1542.4 mm, which is greater than required. Availability is more than the required, therefore safe. You can completely weld it. There is no problem. If at all the length of the weld is available is less than the required, then we have to go with the stiffeners here, stiffener here or here and this side. All this depends upon the designer, as you observed it in the 3D model or in the very beginning of the session what we explained. So now we are going to provide this weld. This is the notation style of providing it. If I show a circle here, it means to say that it is all round welding, and this symbol indicates a fillet weld, and 8 will indicate the size of the weld. So all round welding, fillet welding of 8 mm diameter. This is how the symbol we are going to show it. Now the same problem, if it is the ends are not machined, then how to go about? So in this case, the load we are going to take will be the full complete factored load, axial load that is acting will be taken into consideration, whereas for the machined end it was half of the total load. That's all. That is the difference you should note down. The remaining procedures are same. The calculation part as you observed in the case 1. I'll not explain about this. You have a look on this one once again. The same length. Formula, it works out the same. Equate this to the 1500 load, that's all. So the length of the weld required is once again 1400.45 mm, which is once again less than the availability. Therefore, you can make all round welding, there is no problem. This is the connection details. So in the question, where you just see whether it is given with machined ends or not machined ends, or you can assume yourself and solve the problem. If you assume machined end, take 50% of this load. If you assume that ends are not flushed or it is cut by hand saw, then you go with full load. That's the only difference you can find out. Coming to the concrete block, it is same as what we explained in your bolted slab connections. The total axial load is taken as 1000 kilonewton. We are going to design the dimension of this, the length and breadth and the depth of the section. So here the base plate is rectangular nature, 500 mm by 450 mm. I wanted the larger projection of this one, therefore I am going to take the lower side of the base plate, that is 450 mm, so that I get the maximum projection and get the depth of the section where the load will be dispersed at an angle of 45° from the edge of the base plate. Now let us assume the self weight of the concrete, some 10 to 15% of the column load, which is an approximate value. Actual concrete weight can be calculated by knowing the volume of this multiplied by the density, you will get the actual weight. Now it is an approach we are making, we will go with some percentage of assumption with thumb rules. It is taken 10%, it is 10 divided by 100, 0.1 times of this, it is totally works out to be 1100 kilonewton. Divide this value by the SBC of the soil, you are going to get the area of the concrete block. Whether it is a rectangular slab base or a square base plate, you design a square concrete block. Therefore, the side works out to be 2.57 meters and say make it 2.5 meters. So it's 2.5 meter by 2.5 meter. Let us find out the thickness of the or the depth of the concrete block. So always we know that the dispersion angle will be always 45°. It reaches to the bottom. This depth will be equal to this projection. Here I have taken the lower value to get the maximum projection. It's 2.5 minus 0.45 divided by 2. It's 1.025. Let us make it say 1.1 meter as the depth of the section. The overall size of the block is 2.5 meter by 2.5 meter by 1.1 meter. This is the size of the concrete block required. Now this is the cross section elevation. The column section, the base plate, the concrete block of 2.5 by 2.5. We will provide the anchor bolts here, as we are not designing, since it is subjected to only axial node moment. A minimum of 2 numbers could be given to anchor this bolt, but however in our case we are showing with 4 bolts of anchor bolts provided at all the 4 corners. These are the anchor bolts. That even this could be designed. Now we are providing it nominally when it is subjected to a moment, and when the base plates are subjected to tension, a portion of the base plate sometimes will be subjected to compression and some part will be subject to tension. To keep this in position, not to be lifted up, we are going to provide the bolts. Different types of bolts are there. In that one type of bolt we have shown here, that is J type of bolt connection. This could also be designed for the tension. This is a plan of the complete slab base and the concrete block and the I section. We have provided the 4 corners. The welding has been shown. 8 mm fillet weld all round. The sizes of the column section, thickness of the web, thickness of the flange, size of the base plate 500 by 450 mm, size of the concrete block 2.5 meter by 2.5. This is the final top view of the slab base. If you want to know much about the other types of designs, a link has been provided in the YouTube. You can look into the design aspects in my notes. Thank you for watching. If you are not subscribed, kindly subscribe now. Thank you.